Hello everyone, Dr. Young here, and in this video I'm going to teach you how to draw atomic orbital diagrams. This is going to be a very important skill, one so that we kind of have a better sense of what the electronic structure of an atom is, what's going on with the electrons, what their different energy levels are like, and how they're arranged in space. But this is going to help inform us in the future about bonding, when we start taking atoms and putting them together with things. So this is just how we would talk about the electrons and their energy for simple atoms. We've already had a series of videos, right, going through all of this different stuff, right, about light and atomic absorption and emission spectra and quantized energy levels and the Bohr model, pros and cons of the Bohr model, which we'll come back to, electrons having wave-like properties and how that led to wave functions, and then the square of those wave functions to give us these 3D probability maps of where an electron is likely to be found, and that being described by the four quantum numbers, N, L, M sub L, and M sub S. Now we are going to talk about how to put this all together in sort of a simpler electronic diagram for those electrons. So we're going to have an atomic orbital diagram, and we'll add electron configurations to the next one. So really, we're kind of here. We're like at 7.5, which is atomic orbital diagrams. So I'm going to link these atomic orbital diagrams to our four quantum numbers, right? You've already seen this all before. Oh, I need to put my spin up, spin down, right, for my electrons for the M sub S. But I'm going to point out when we draw these atomic orbital diagrams how we can get the M, the L, the M sub L, and the M sub S for any given electron in that atomic orbital diagram, right? These are supposed to go back and forth. We use these numbers to build the atomic orbital diagrams, and those atomic orbital diagrams should also be able to give us those numbers back. And by atomic orbital diagram, I don't mean that you have to draw out the shapes of the orbitals. I just want a diagram showing me the relative energy levels and the ordering at which you find these, right? We talked about how we have s orbitals, we have p's, we have d's, and we have f's. And so we're not going to have to draw these all out. Maybe I'll put some of these shapes on the atomic orbital diagram so you can kind of see them. But you don't have to redraw these shapes. You don't have to memorize these shapes. You should know things that like S is spherical and that P's are shaped like dumbbells, and then D's get more complicated. They're kind of like four-leaf clovers until you get real weird, and then F's are even weirder. So we don't have to go too crazy into that. To draw an atomic orbital diagram, I've kind of already shown you some in previous videos, but you just need to say what orbitals are needed to get to that atom on the periodic table, and then you fill that in with the appropriate number of electrons. So in this example, I am doing nitrogen, right? I'm doing a nitrogen atom. So I'd look on the periodic table. I know that nitrogen's right here. Let me draw this in black. I know nitrogen's right here on my periodic table. And so what we're saying, right, is that you have to start with the 1s block, right? So you start with your 1s block. So you have a 1s orbital, then you go to your 2p's, or sorry, your 2s's. Then that hits the 2p's, and that's where nitrogen is. And remember that p's are, the p subshell has 3 orbitals in it. They're all degenerate. They all have the same energy levels. And I put these in order, right, of their increasing energy. As I go down the periodic table, every subsequent orbital gets higher and higher in energy, generally speaking. And so for nitrogen, I just had to get there. I didn't have to go into the D block or the F block or anything like that. You just needed to go into the 2p block. And then notice that I also said you have to get to the appropriate number of electrons. And by the appropriate number, I mean for that atom, right? So here we have a nitrogen atom. And what you want to keep in mind is that atoms are neutral. And if they're neutral, that means that they have the same number of protons as they have number of electrons, right? They have the same number of positive things, which are protons, and the same number of negative things, which are the electrons. So in a neutral atom, the number of protons and electrons are the same. We are not talking about ions yet. We will talk about ions in the future. Right now, regular atoms, number of protons equals the number of electrons. So for nitrogen, since it is number 7, it has 7 protons, which means therefore we have 7 electrons. So I need to put 7 electrons into these orbitals somehow. And the rules for how I put them in are called the Aufbau Principle, the Pauli Exclusion Principle, and Hund's rule. Those are the rules that we're going to follow. So I'm going to walk through each of those rules with you. So we just said, right, that I need to fit 7 electrons in here. That's the number of electrons, so 7. And what I'm going to do, right, I have all these different orbitals that nitrogen might have. I have the 1s, 2s, 2p. I put the 3s here. We're going to end up not using it, but I wanted to emphasize just that all of these orbitals exist for any given atom. You just might not fill them. So normally we just go up to the ones that we need and we ignore all the ones that are higher energy, but really they are there. And I'll talk more about that later. When you excite an electron, it needs to have an orbital to go into, for example. So the first thing I do, I'm gonna look at Aufbau Principle. The Aufbau Principle just says that you fill your orbitals lowest energy first. So for the Aufbau Principle, Aufbau I think is German for just like from the bottom up, like you'd build a house from the foundation first, and then the house on top of it. So it's like building from the bottom thing is what Aufbau is supposed to mean. So for us, though, with these, it just means that you fill the lowest energy orbitals first. Right, and for us, the lowest energy orbital is the 1s, right? It's the lowest energy orbital. The 3s is my highest energy orbital that I have drawn here. So Aufbau just says put your first electron in there. And what we do with our first electron is we always do it spin up, right? So I put my 1 electron in there. It is spin up, which means it has an m sub s equal to positive 1/2. So I drew the spin up, that little one-headed arrow thing. Now, that's one of my 7 electrons. I need to do 6 more. So where does the next one go? Remember that all of these orbitals can fit 2 electrons, and I'll write that here to this, not for the Aufbau principle, just in general, right? Remember that all orbitals can fit 2 electrons, right? So this 1s, I only have one electron in this orbital. I can fit a second one in there. So let's talk about how we fit that second one in there, because that has to do with the Pauli exclusion principle. All right, so again, I got to fit my 7 electrons. We already said my first one's going to go in the lowest energy one because it's following the Aufbau principle. The Pauli exclusion principle basically just says that no 2 particles and for us, the particle we're looking at is an electron, but technically this is also true for protons and neutrons and other things, but no 2 particles in general can have the same 4 quantum numbers. Right, so every particle is going to have its own set of 4 quantum numbers that are unique. So the Pauli exclusion principle is what we're saying is that once a set of quantum numbers is used, it is excluded from being used by anything else. You can't use those same 4 quantum numbers. So that means that when I put my second electron in here, I cannot have it be pointing up also. Because if I did that, what we're saying now is that for these 4 quantum numbers, right, for this electron, the 4 quantum numbers would be 1 for the principal number, right? So this is my n, my l, my m sub l, and my m sub s. My n is 1 because this is a 1s. My l is 0 because it's an s orbital. My m sub l is also 0. That's the only allowed value. There's a 0 here. And then my m sub s is plus 1/2 because it's a spin up. If I look at the second electron, I get the same set of quantum numbers, right? It's in the 1 principal number. It's a s orbital, hence a 0. All s orbitals only have a 0 for their magnetic quantum number. And then it's also up, which gives it a plus 1/2. This would violate the Pauli exclusion principle. They have the same quantum numbers. So how do we fix that? The fix is really easy. I just make my second one spin down instead. So instead of being 2 spin up, I have 1 spin up, 1 spin down. And if you look back at the previous videos, maybe you already have this in your notes, I did that always, if I put 2 electrons in a single orbital, one was up, one was down. And if my second one is spin down, then that means that changes these quantum numbers over here, so that now I have 1, 0, 0, negative 1, whoops, in blue, negative 1 for the second, right? So now these have a different set of 4 quantum numbers. I have 1, 0, 0 plus 1/2 for that one, and 1, 0, 0, negative 1/2 for that one. So I've not violated the Pauli exclusion principle. And so first I put the electrons in the lowest energy value. If I need to pair them up and make sure they're opposite spins, that's what the Pauli exclusion principle is saying. And then I can keep going, right? So I need to get 7, I only have 2. So that's my 1, 2. Now I move up to the next one because that's my next lowest orbital. So 1, 2, this is 3. And then I do 4. So I've got 1, 2, 3, 4. And then I keep going up 5. And now this is where our next question is, right? My 2p's are degenerate. Remember that degenerate orbitals just means that they're orbitals that all have the same energy. So the 2p's has 3 degenerate orbitals. So what do I do with my second one? Does my next one pair up, right? Because that's 1, 2, 3, 4, 5, 6. I need to get 7. Do I do this so that I get 7 electrons? Or do I spread them out like this? Right? Because that's also 1, 2, 3, 4, 5, 6, 7. What's the correct way to do this? And it turns out that's what Hund's rule is going to tell us about. So for Hund's rule, that's going to solve our problem, right? So I've got 1, 2, 3, 4, 5, but my question is, where do I put my 6th and my 7th? And Hund's rule basically says, basically you fill a subshell, like the 2p, for example, the 2p subshell, fill a subshell singly before pairing up electrons. Before pairing up electrons. So that means that I would go 1, and then I'd do this one singly, and that one singly, and if I had more, then I would go back and start pairing, and start pairing, and start pairing. So you'd fill it singly first before you start pairing. So I do not, right, if I was to add electrons, I do not add them like this. I do not go, well, let's do a pair, and then another pair, and then my other one, right? We fill singly first across, then we pair if we need to. That's what Hund's rule is saying. So for this one, what do we have? We got 7 electrons. So I've got 1, 2, 3, 4, 5. I've got 4 drawn. So 1, 2, 3, 4. Number 5, number 6, number 7. That's what the atomic orbital diagram for nitrogen would look like. I ended up not pairing any electrons in the 2p, and that's fine. This is what the nitrogen atom's ground state would look like, is the idea. Now, Hund's rule, the reason why we fill a subshell singly before pairing up electrons is because of something called pairing energy. And basically, this is the energy cost of putting 2 electrons in the same orbital. So normally it's a relatively small amount compared to your jump from, like, say 2s's to 2p's. But if these are all the same energy level, then it's going to be more energetically favorable to not pair up if you don't have to. Because there's no cost in putting your second electron here and your third electron here. There's no cost there. These are all equivalent in energies. But if I had tried to pair, right, you're putting 2 negative things in one orbital in one small space. There's some energy cost to that, to get those 2 negatives to be in the same orbital. So we try to avoid it if we can. That's what Hund's rule is about. Once we can't avoid it, then yes, you start pairing them up. It costs a little energy, but you can start pairing it up. So Hund's rule says you fill a subshell singly before pairing up, and that's because you're trying to avoid pairing energy. Let me put that in quotes. Pairing energy. Now, so then we have, right, like I said, this is the ground state for nitrogen. Ground state atomic orbital diagram for nitrogen. Notice that I didn't put anything in this 3s, and there'd be 3 P's that are up here that I didn't draw, and there's 4 S's and 3 D's and 4 P's, etc. But I just didn't use them, so normally we don't show them. So it's totally fine if you wanted to just completely ignore this one and just like erase it. That would be totally fine if you wanted to do that. So let's talk about a bigger, more complicated atom. So let's go with manganese, right? Manganese is much bigger. Manganese is over here. It is, right, 1, 2, 3, 4, 5. Here's manganese, Mn. So it's in that D block. It is number 25. Its atomic number is 25, which means it has 25 electrons. And so I need to build my energy diagram. I need to say, well, what orbitals is it going to use? And I need to fill in those electrons. So again, we read the periodic table like normal, left to right, top to bottom. So first I fill in my 1s, and then my 2s's, and then my 2p's, and then my 3s's, my 1,3s, now my 3p's, and now my 4s, and my, looks like I'm in my 3Ds now, 1, 2, 3, 4, 5, 3Ds, right? To get to where manganese is. Again, technically it has more orbitals than this that just don't have electrons in it, but no one bothers putting like the 4 P's and the 5 S's and keeps on going. Technically they're there, they're empty, we don't need to worry about them. And now I need to put in these 25 electrons, and so I'm going to follow the Aufbau Principle, the Pauli exclusion principle, and the Hund's rule. So I'm going to go 1, 2, start lowest, and notice I pair them oppositely just like we did before. So 1, 2, 3, 4, 5, 6, 7. I'm following Hund's rule, right? I went across the P's, I didn't pair them up yet. But after I get past 7, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. That is what it would look like. I got all 25 of my electrons. I filled the 1s. I filled all the way up to the 4s. And then my 3D is half full, right? I could have fit 10 electrons in there, but I only needed to put 5 in to get up to my 25. And so this is what the atomic orbital diagram for manganese would look like, following those same rules, right? Following those exact same rules. Now this is kind of a lot. You can imagine, right, I'm doing relatively smallish things. Manganese is nowhere near halfway through the periodic table. As you get really larger, when you get down to things like gold, or heaven forbid you get into the F block and you're doing things like uranium or something like that, this gets really, 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 really unwieldy really quickly. It gets so big. And so what we can do is we can talk about just the valence electrons, right? So this is the whole ground state. This is the ground state. Ground state AO diagram, right, for manganese, Mn, not magnesium, manganese. And this is kind of a lot. What we can do is talk about just the valence electrons. And the valence electrons are just the outermost electrons. The valence electrons are just the outermost electrons. So we're talking about the last row, the last period. So that means for manganese, the last period that I did is period 4. 1, 2, 3, 4. This is the last period that I did for manganese. That means that these are the valence electrons. Or another way to say it is that what I can do is I can get away with not talking about any of these, right? That these right here are the valence electrons. I can talk about just the 4s's and the 3d's and ignore all of these in here, which we would call the inner shell electrons or core electrons. So inner shell or core electrons. And what we can do is we can just abbreviate all this inner shell, inner core stuff by the noble gas that leads up to there. So by noble gas that leads up to there, I mean this, whatever this is right here. And if you look at your periodic table, that's argon. You can't really see that here, it's argon. So I can abbreviate all of these just by saying argon plus these other things. And I'm gonna redraw this so you can see this a little bit better. But that's how we can abbreviate some of these really, really big atoms, is we can just show the valence electrons. So let me redraw this, clean this up a little bit for you. All right, so what I'm saying for manganese, so if I don't want to draw the whole thing, I can draw an abbreviated atomic orbital diagram, where I just start off, right? Remember that we said manganese was here. Here's your manganese. Sorry, this is so small. I've got argon is noble gas beforehand, and we're said that, oh, this is just so big, I want to just draw the valence electrons. So you can start off and just say, oh, hey, by the way, all the stuff that argon has, all the electrons that argon has, plus my 4s and my 3d. And then fill in appropriately. But that means then that you have to just count the electrons that would be in those orbitals. So that'd be 1, 2, 3, 4, 5, 6, 7. And what you can do if you're real clever about this is, I know that there's 7 valence electrons because there's 7 spots to get to manganese. This is 1, which I've drawn this bigger. 1, 2, 3, 4, 5, 6, 7. Right? So where manganese is, it's in the 7th box on the periodic table. And so I know there's 7 valence electrons. I'll write that. 7 boxes over. Sorry, I'm going to clean up that. Seven boxes over means it has 7 valence electrons. So those are the ones, again, in that outer shell, that highest energy shell, the ones that are just on the outside that we're trying to abbreviate this with. So if you ever see something like this where it's like, wait, why did someone write argon in the middle of this? I thought we were talking about manganese. It's because they're saying, instead of drawing all of these electrons that go before here, you just say, oh yeah, it looks like argon, but then you also go to the 4s and the 3d, and so you kind of continue from there, is the idea. And we'll use this nomenclature a little bit more when we do the electron configurations. Now again, keep in mind, I'm going to do this one more time. I want you to be able to connect, right? I want to know what are the quantum numbers for this electron and what are the quantum numbers for, say, this electron, right? So, and again, you were talking about the N, L, M sub L, M sub S. This would be a good place to pause, see if you can do these 4, right? Can you write the 4 quantum numbers for that electron? So if we go through this, the N is 4, right, because it's a 4s. The L, again, is 0 because it's an s orbital. The M sub L, there's a 0 here, is L. And that electron is spinning down, so I say minus 1/2. So 4, 0, 0, minus 1/2. This one over here on the right-hand side, its principal number is N, well, it is N, but it's 3, because it's a 3d orbital. For D, right, remember that when L is 0, that was an S. When L is 1, that was a P. And when L was 2, that was a D. So that means this is a 2. For the next quantum number, remember that we go -2, -1, 0, 1, 2. So if I'm talking about that one, it's in the -1 orbital of that subshell, and it's spin up, so it gets a plus 1/2. Right? So this -1 right here came from the fact that it was here. If I was pointing to this arrow, it would be a +1 right there, or a +2 if it was this one. So all of these numbers should make sense going forwards and backwards is the idea. So what I'd like for you to do is to pause right here, and I want to see what you can do with sulfur. Right? So good old sulfur, it's number 16. Number 16 on the periodic table. So see what orbitals you can. Just do the whole thing, don't abbreviate it, just do the whole atomic orbital diagram. See what you can do. Okay, so hopefully you paused and took a crack at this. If I was going to draw this, right, I've got my energy up here. You start filling like normal. So always the 1s, and then the 2s, and then the 2p, and then the 3s. And then, because we're in the 3rd row, right, so I had to go through all of these. Looks like we're in the 3p's, so I have to go all the way up to the 3p's. How many electrons do I put in here? Well, if that's number 16, then that means there's 16 electrons for sulfur. And then I start filling from the bottom and I start going up, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then I stop. I really want to do another one. Blink. 16. So sulfur would look like that. Right? That's your atomic orbital diagram for sulfur. Again, I don't care that you draw the shapes of a lot of these things, right? I'll draw them just to kind of, again, help you connect what we're doing with like physical 3D probability maps. But what we're saying is that this 1s orbital is this spherical orbital like this around a nucleus. The 2s is also spherical, but it's bigger than the 1s. Then we've got the 2p's. Remember that the 2p's, those are, there's 3 of them because they go in 3 different directions, right? They have an up-down one, they have a left-right one, and then they have one that's kind of coming out at you. And so we usually kind of draw like this little sort of deal where it's coming out at you, right at your face. So that purple part would be coming out at your face and the white part would be going back. And then we have a 3s, which is bigger yet. And then we have the 3p's, which are the same thing, but again, bigger, right? So you have these bigger, oh, now I'm just going to get messy, but you know what I'm saying. And they have inner lobes into them also, right? So we're saying that these are where you have electrons, and these are the orientations of the orbitals, and here's the orbitals that are full, right? So for example, I don't have any d's, right? So if you look at a d orbital, like this, I don't find any electrons that are in an orbital that has that probability map, that has that shape, right? That's something that I know about sulfur. I don't really see that. None of these ground state electrons look like that. So that's how you draw atomic orbital diagrams. These are all the ground state ones. In the future, what I will do is I will talk to you about how you excite them. We already kind of talked about that with Bohr, but you can excite electrons in these also, right? That whole idea still applies. It is, in fact, what you were really seeing when you saw atomic absorption and atomic emission, is that you can excite electrons from these ground states into higher energy levels. So we'll talk about that in the future too. But first, we're going to talk about how to write, briefly, how to write electron configurations, which are pretty straightforward. You just say how many electrons are in something. So to give you a preview, electron configuration, this would be 1s, but there's 2 electrons in the 1s. And then you have 2s's, there's 2 electrons in those. Then you have the 2p's, there's 6 electrons in those 2p's. Then you have the 3s's, there's 2 electrons in those. And then you have the 3p's, and it looks like there's 4 electrons in those. So we're going to talk about how to draw those next, and that would be electron configurations. So definitely practice this stuff. I've posted worksheets on the webpage and everything. Practice, practice, practice. Watch the next video. Happy studying.